Hi, this is Jonathan Gardner. This is section 532 of Griffith's Introduction to Electrodynamics, second edition. This is a rather mathematical, we're just going to do a bunch of math. Hopefully I won't make too many mistakes. We're going to calculate, starting with the Biot-Savart law, the divergence and curl of B for the general case, for every possible case you can imagine. So starting with the Biot-Savart law, we have the B vector in the volume current, mu naught over 4 pi, that's always there. The integral of J vector cross r hat over r squared d tau. Now, there's going to be some funky business involving the grad, the del applied to J vector, and so we have to be very clear here. So B vector is a function of x, y, and z. Okay. J vector, however, is inside this integral. We're not interested in the J vector at B. We're interested in the J vector for this integral. So this is actually x prime, y prime, and z prime. So this is inside the integral. Okay. R vector is equal to x minus x prime, y minus y prime, z minus z prime. And I should not write it that way. I hat, j hat, k hat, add it together. Okay? And d tau is inside the integral. This is dx prime, dy prime, dz prime. Okay, so now I've laid some ground rules. So we're going to apply the divergence to this equation. So we're going to take the divergence of B. Divergence of B vector is equal to the divergence of all this crap. Well, mu naught 4 pi is just a constant factor that's going to survive. And then we're going to take the divergence of J vector cross r hat over r squared d tau. Okay. So we're going to take product rule number 6 inside the back cover of your book. Turn to that. Product rule number 6 states that the divergence of a vector cross another vector is equal to the second vector dotted the curl of the first vector minus the first vector dotted with the curl of the second vector. Okay? So looking at this, this is indeed the divergence of a cross product where A vector is J and B vector is R hat. Okay? And this R squared is really just a factor that you can pull out, but only you have to keep it inside the integral. And so we have the divergence of J vector cross R hat. Let's put the R squared over here just to be sanitary. Well, that is the second vector dot, so the second vector is r hat over r squared dot the curl of the first, okay, minus the first vector dotted with the curl of the second. Okay, now bear in mind that this curl that we're taking, this operator, is not in terms of x, y, x prime, y prime, and z prime, but x, y, and z. How does the J vector vary in respect to x, y, and z? The answer is it does not, right? So this term right here is 0 because the J vector doesn't vary at all. We're going to use the same J vector across this integral whether or not we're evaluating at one spot or another spot, okay? And so it doesn't vary at all with respect to x, y, and z. So if you change x, y, and z a little bit, J vector doesn't change at all. Okay. But the second one is this is the curl of r hat over r squared. Okay, and that if you went back to chapter 1. There was a problem about what the curl of vector fields that look like this are, and the answer is that the curl is 0 as well. Okay, so this one is 0 as well. So the divergence of B is equal to the integral of 0. So the divergence of B is 0, thanks to product rule number 6 and our meticulous accounting for variables. Okay. The next thing is, let's find the curl of B. So the curl of B is equal to the curl of that stuff. The curl of the cross product of r hat over r squared d tau. Okay, let's do the same exercise here. So let's take product rule number 8, which states, product rule number 8 states that the curl of a cross product of two vectors is equal to b vector dot del a vector, okay, and then minus, oh, this is not going to be easy, a vector dot del b vector. What the heck are we doing here? Well, the answer is this is a dot product which leads to a scalar. So this is basically bx d by dx plus by d by dy plus bz d by dz. Okay, and the same thing over there. And then we add in the a vector times the divergence of b. We subtract the b vector times the divergence of a vector. Alright, so we have 4 terms there that we need to account for if we're going to properly calculate the curl of B. So let's write this out with this dude. So we have the curl of j vector cross r hat over r squared equals, well, we take the second one, that's r hat over r squared dot del times j vector minus j vector dot del times r hat over r squared plus j vector times the gradient of r hat over r squared minus r hat over r squared times the divergence of j vector. Okay. Which ones can we cross off? Well, again, this is an operator operating according to d by dx, not d by dx prime, but d by dx, d by dy, d by dz. So anytime we have this thing interacting with the j, we can say that that's 0. Okay, so here we have, this is going to be 0. Okay, and then this dude right here is going to be 0 as well. Okay. This guy and this guy, however, will survive because R has X, Y, and Z in it, as you can see here, X, Y, and Z. So there will be some something left when those are done. Okay, so we have this is equal to, let's write it out this way, j vector times the divergence of r hat over r squared minus j vector dot del, I'm sorry, of r hat over r squared. Okay. The divergence of r hat over r squared, we did an entire section on this in chapter 1. The answer is the divergence of r hat over r squared is 4 pi, the Dirac delta function in 3 dimensions of the r vector. Okay? This is just j times that. Okay? The net result of that is we're going to plug this back into that integral. And basically the only value that's going to survive when we plug that back in is going to be j at r. Right? So let's do that right now. So let's take this term, let's plug it into here. So let's do this. Okay, so let's stop there. Let me draw a box here so I can remember to do these later. Okay. So let's take the integral mu naught over 4 pi of the integral here d tau. So we're just plugging this one term, we're going to separate the integral out to that way. Okay, so then we have mu naught over, well, the 4 pi's cancel. So we have integral j times the Dirac delta function of r d tau. What's that equal to? Well, that just picks out j at r. This is mu naught j vector of r vector. Okay, very straightforward. Hold on, I'm not quite doing that right, am I? No. R vector is, this is the same as r vector minus the r prime vector. R prime is the one with x prime, y prime, z prime. And so this actually picks out the r vector. J vector at r vector. Okay, so this first term that we get from this integral gives us this. Okay, a hint, the second term is going to be 0. We got to show why that's 0 on this next page here. So let's do the second term. So we have mu naught over 4 pi, well, negative, we have a minus sign here, integral of j vector dot del r hat over r squared d tau. Okay, is this guy equal to 0 or not? Because we're acting on this little funky guy, okay, and this is kind of a stretch if you don't buy why this works. Okay, so if we had, so this guy is equal to d by dx I hat, well, I should put the hats in front, j hat d by dy plus k hat d by dz. This dude is going to be equal to I hat d by dx prime plus j hat d by dy prime plus k hat d by dz prime. Okay, so whatever this guy is, we take this function and notice that, you know, r vector is equal to r vector minus r prime vector, right? So negative this guy is going to be equal to r prime minus r vector, right? So if we took the regular derivative of this guy, it's going to be operating on this first one. If we took this guy on this dude, it'll be operating on the first one. They're going to be equivalent, okay? So we can say that, you know, something del operating on r vector is going to be equal negative del prime acting on r vector. Okay? So this guy is actually equal to mu naught over 4 pi integral of j vector dot the prime del, using the, you know, x prime, y prime, z prime, of r hat over r squared d tau. Did you buy it? I hope you did. If you didn't buy it, shame on you. You need to do some more work until you do buy it. Okay, let's look at one component. We're going to look at I hat. Okay, so I hat. So that is going to be, let's do j. Okay, so he does this way. All right. This is the step that, okay. The x component in particular. So we have j vector dot del prime of x minus x prime over r cubed. Okay, that's the I component, the x component. So let's use product rule number 5. We seem to use 5 more than anything else. Number 5 states that the divergence of some scalar function times some vector is equal to that scalar function times the divergence of that vector plus that vector dotted with the gradient of that scalar function. Okay, so here we have a scalar function. Here we have a vector. So vector dot the gradient, right? So we can, this is that second term there. So this is equal to the divergence of the two multiplied together minus the function times the divergence of j vector. Okay? The divergence of j vector in steady currents is 0. 0 for steady currents. If we can just now prove that this is going to be 0, then we can use the same reasoning for any other coordinate in our vectors. Okay? So the contribution to the integral is going to be the integral across that surface of that times x minus x prime over r cubed times the j vector d tau then this is a volume integral, of course. We're going to apply the divergence there to reverse this into a surface integral of drop the del, the divergence, x minus x prime over r cubed j vector dot dA vector. Okay. And the question is, what surface are we integrating over? Well, let's say that the volume that we're integrating is all space. We just make it bigger and bigger and bigger until we eventually have all space. What is the volume current out there on the edge of space? And the answer is, well, unless you have infinite currents, which we're not going to deal with, then this has to be 0. Okay? So we've proven that the second term of, so we've started off proving quite simply that the divergence of B is 0, because using product rule number 6, it's 0. Okay? The divergence of B is 0. Then the cross of B, we took this guy, broke it into two terms using product rule number 8. The first term, when we integrated that, gave us mu naught j at r. Okay? The second term, if we use a volume that's large enough, will give us a 0, right? And so we can safely say that the cross of B is equal to mu naught j vector at that position. So now we have the end result of this mathematical fun and games, namely that the divergence of B is 0 and the cross of B is the volume current at that point times mu naught. Thanks for your time. I hope I wasn't too boring. Bye.